Up to this point, we have been considering systems that are going to equilibrium. What we're going to do now is different. We're going to take a system that's already at equilibrium and throw it out of equilibrium, and then we'll predict what will happen. We can do this by adding or removing a substance from the equilibrium mixture, or by changing the temperature. This gives you, the experimenter, the ability to manipulate an equilibrium. We are going to use a principle called LeChatelier's principle. Again, we start with a system that is already at equilibrium and then change the conditions. We'll change the concentration of one of the components of the equilibrium, or we'll change the temperature. What LeChatelier's principle states is that the system will eventually go back to equilibrium. That's actually a pretty easy concept, but the question for us is how. Let's think about concentration changes. What we, the experimenter, can do is to add a substance or remove a substance. This changes the concentration of one of the components of the equilibrium. We know the system will go back to equilibrium, but there are two questions that we can ask about how this happens. We can ask which way the reaction shifts, to the left, converting products into reactants, or to the right, converting reactants into products. We can also ask how the concentration of another one of the components of the equilibrium responds. Does it increase or decrease? Let's think about what happens if we add a substance to a system that is at equilibrium. We've now thrown it out of equilibrium, and in order to get back to equilibrium, the system needs to get rid of what you have added. Now, the system can't throw that material back out of the beaker. The only thing it can do is react that material away. Let's use the example of combining dinitrogen and dihydrogen to form ammonia. Let's ask what happens if we add H2. Which way will the reaction shift? The system will react it away by combining some of the added dihydrogen with dinitrogen to form ammonia. In other words, the system will shift to the right. Using the same reaction, what if, instead of adding H2, we add ammonia? Again, the system will try to react it away, taking some of the added NH3 and forming N2 and H2. In this case, the reaction shifts to the left. The other way we can ask this question is, how does the concentration of dinitrogen respond to these two situations? In the first case, where H2 was added, the reaction shifted to the right, combining N2 and H2. Since dinitrogen is used up in this shift, the concentration of N2 must decrease. In the second case, where ammonia was added, the reaction shifted to the left in order to remove some of the added ammonia. When that occurs, more dinitrogen is formed, so the concentration of N2 must increase. As experimenters, we can also remove a substance from a reaction mixture. For example, in a gas phase reaction, we may be able to condense out one of the gases. Or with a mixture in solution, we may be able to add a reagent that precipitates out one of the components. If a substance is removed from a reaction mixture at equilibrium, the system will react in order to replace what was removed. Going back to our ammonia reaction, if we were to remove dihydrogen from the mixture, the system would try to replace it. To do so, ammonia would be converted to dinitrogen and dihydrogen, shifting the equilibrium mixture to the left. Again, using the same reaction, if we were to remove ammonia, the system would try to replace it by combining N2 and H2, shifting the reaction to the right. We can also ask what happens to the concentration of N2 in these two situations. In the first, when H2 is removed and the reaction shifts to the left, more N2 will be produced, so the concentration increases. In the second, when ammonia is removed, the reaction shifts to the right, using up some of the dinitrogen present, so its concentration decreases.